Hi, and welcome to our next section where we will play with clustering. In this section, we will learn how to use unsupervised clustering algorithms to build similar groups. We will review the available clustering Spark algorithm and apply k-means to group by followers and friends. We will also group by location and try streaming k-means. Now we move on to the first video of this section that introduces you to clustering with Spark. In this video, we are going to take a look at different clustering algorithms Spark provides. We will take you step by step to prepare data and train a k-means model with the mllib class. Then we will display the clusters with the embedded Zeppelin widget and with mllib. Finally, we will see how to evaluate the models. Clustering algorithms attempt to find groups in datasets. Spark provides various variants of the k-means, including bisecting k-means and streaming k-means. K-means clustering is a very well-known algorithm. It tries to detect k cluster in a dataset, where k is a given parameter. K-means defines its clusters to minimize the sum of squared errors or distances within each cluster. This objective function is named the within cluster sum of squared errors, or WCSS to make it short. K-means initialization is made on a random basis. You can read more about k-means on wikipedia.org/wiki/k-means clustering. Spark provides an optimized variant that deals with the parallelization. Upon to k-means, Spark ships also Gaussian mixture modeling, GMM. It also ships power iteration clustering, PIC, and also latent Dirichlet allocation, LDA. Those algorithms are both available in mllib and ml packages. Time to try the mllib k-means implementation. Like usually, let's load our tweet reference dataset. The mllib k-means expects a RDD of vector. As we want to cluster the number of friends and followers, we create the data variable which contains all occurrence of the user object for all tweets with the columns friends count and followers count. We could argue if we would need to group by user and take the latest seen information or a mean of that information. For the simplicity, we take here all collected information and we emit an mllib vector with a number of friends and followers. We call now the train method on the k-means object, giving the data we want to cluster. We specify the number of clusters and the number of iterations, and we get back the trained model variable. With the trained model, we can create an array of points to plot. The Zeppelin built-in widget is easy to use for this. Please note that the number of plotted objects are limited, so depending on the size of your dataset, you may have to sample. We could also put the points into the Zeppelin context and send it to Python. And we can plot it with matplotlib. We also want to evaluate our model by computing the WSSCE, so the within set sum of squared errors. For this, you just have to call the compute cost method on the created model, passing the data. An interesting question is the number of clusters we need to request. We have just set the k to an arbitrary value. To have a better view, we can create the elbow graph, which shows the WSSE per iteration count. Typically, the graph will flatten quickly, and you know that you can limit the number of iterations at the elbow of the graph. In this video, we have clustered user per followers and friends with the mllib package.